All right, everybody. So today's lesson is focused on 8-5. So chapter 8, section 5. The title is variation functions. So there's three different types of variation functions. Pretty easy concept. So you can see them straight across the top in your table that you see. So we got direct variation, joint variation, inverse variation. And these are their corresponding equations. So direct variation is just y equals kx. Joint variation, y equals kxz. And then inverse is just y equals k over x. And I may teach this a little differently than you may have seen it from your teachers, but this is just the way that I go about it. I tell my students, remember those equations, okay? And if you just kind of compare all three equations, you notice that they all have a y. They all say y equals. They all have y. They all definitely have x. So the joint variation just has that additional variable of z, but the most crucial point is k. K is vital. And what K is called the constant of variation. So, and this is just kind of the way that I teach it. K is your constant of variation. Okay, if you go across this next row, this is just basically another way to solve a direct variation, a joint variation, inverse variation. But again, I teach it possibly different than what your teacher told you. Okay, but the keywords are underlined, so if a problem were to say that y varies directly as x, then you want to use the direct variation equation, y equals kx. If it says that y varies jointly as x and z, then you want to use the joint variation equation, y equals kxz. Inverse variation, y equals k over x. Just remember which equation goes with what. Okay, so here's how this kind of works. So number one, pretty easy concept though overall. So number one, it says that if y varies directly as x. So first, I know what equation I'm using. I'm using just y equals kx. It tells you that y is 9 when x is 6. So I'm going to plug those numbers in. I'm going to pause right here. I'll continue on with the rest of the problem in just a second. But again, y is 9 when x is 6. So if I plug these two numbers in, stop here now and solve for k. Again, as I said, k is one of the most vital, crucial parts of the whole entire problem. So if I solve this for k, I just divide both sides by 6. So k comes out to be 9 over 6. Reducing that down, k would be 3 over 2. All right, so we're going to use k now for the last part because it's called our constant of variation. So k is not going to change. K is constant. So using that k value, now we want to find y when x is 8. Okay, so we're plugging it back into the direct variation equation. But again, we're finding y, so we don't know what y is. We know k is 3 over 2, and x this time is 8. So I'm just going to plug them back into y equals kx. So to solve for y, we're really just multiplying k times x. 3 halves times 8. So 3 over 2 times 8 would be 24 over 2, and that would just be 12 is my final answer. Okay, so same thing for the next one, for number 2. It says y varies directly as x, so I know I'm using direct variation, y equals kx. Y is 16, x is 36. Again, pause, solve for k. I'm going to divide both sides by 36. So dividing by 36, and again, reduce down the fractions, 16 and 36. You could divide those both by 4. So k would just be 4/9. And I suggest use the fraction. Don't use the decimal of k. Because if you use the decimal, it comes out to be, I think it's like 0.4 repeating. So you don't want to use repeating decimals. Use the fraction 4/9. Okay, because now we're going to use k for the next part to find y again when x is 54. So plugging back into direct variation, we're finding y. K we know is 4/9, and x is now 54. So going through and just multiplying, solving for y, you should get y equals 24 in the end as your final answer. Because again, you could cross cancel a little bit, cross cancel those down, so really just 4 times 6, you get 24. Okay, the next one, if y varies again directly as x, so we're using the same equation again, y equals kx. They kind of switch it around. They say x is 15 when y is 5, so just make sure you plug them into the right spot. We're trying to trick you on this one, but x is 15, so make sure you plug that in for x. Y is 5. Again, solving for k, divide both sides by 15. Reducing down the fraction, that's 1/3. Again, use the fraction because, once again, this would be a repeating decimal if you use the decimal. And this time, though, switching it up, it says to find x when y is 9. So when you plug this back in, y is 9, and now we're solving for x. So just a little different. Solving for x, we know you don't divide by fractions, you multiply by the reciprocal on both sides. So canceling that out, so you'd have that x is equal to 27 as your answer. And the last one, so if y varies again directly as x, so y equals kx, that's the equation we need. X is 33, y is 22. So I'll just plug this in. Again, solving for k right now. So k would equal 2/3. Just divide those both by 11. And now use k for the last part. Finding x when y is now 32. So plugging this all back in, you'd have 32 equals 2/3 x. Okay, so again, we need to multiply by the reciprocal, which is 3/2 on both sides. So this comes out to be x is equal to, so 3/2 times 32 ultimately will be 48 is our final solution. Because this would just be a 1, that'd be 16. 16 times 3 is 48. All right, pretty easy, right? So using those equations. But now what does this look like graphically? So it says y varies directly as x, and y is -15 when x is 3. So now we're going to graph direct variation. So again, it's just y equals kx, right? Y is -15 when x is 3. So solving for k, you get k is equal to -5. Okay, so we have our k. We're pretty much done. Now it says to write and graph the direct variation function. So since k is -5, when you plug that back in, you have this equation, which just looking at that, we should recognize what that's going to be. It's just a line in slope-intercept form. So if you just compare it to y equals mx plus b, so direct variation is essentially just a line in slope-intercept, except the b is always going to be 0. You're never really going to have a b. So as far as graphing this, if I want to graph y equals -5x, I'm starting at the origin. That's my y-intercept. And now just going down 1, 2, 3, 4, 5, and to the right 1. This would be the equation y equals -5x. Okay? So last one down here at the bottom, the cost of an item in euros E. It varies directly as the cost of item in dollars D. So let's just set this up. So again, we have y equals kx because it's direct variation, but let's use their variables. They say that E varies directly as D. So that'd be that E equals k times D. The euros varies directly as dollars D. It says 3.85 euros when you have $5, 5 US dollars. So we want to know how many US dollars would I have then if I had 10 euros. Okay, so again, find k first, plug in the first two values you have. You have 3.85 as E. That's equal to k times D, which is 5. So solving for k, divide both sides by 5. I got that k comes out to 0.77. So there's my constant of variation. Now use that, plug it all back in. Again, how much money would I have in US dollars if I had 10 euros? Plug this all back in. So 10 is E. We have 0.77 for K, solving for US dollars. So dividing both sides by 0.77. And it should come out to, if you round this to the nearest penny in US money, this comes out to be about $12.99. So pretty close to being 13 full dollars. All right, so there's direct variation. On the next side, so this says if y varies jointly as x and z, so here's the equation you're using. So I just like to jot down the equation first, and then I'll just plug it all in after. So it says find y when x is 10 and z is 5, if y is 12 when z is 8 and x is 3. So the finding part is actually listed first. This is what we're going to do at the last part of the problem, is find y when x is 10 and z is 5. But we first need to know what k is. So we're actually using this latter part of this problem, the second part that's given to us, plugging in these variables. We have 12 is y, x is 3, z is 8. So you'd have 12 equals, that's just 24. And dividing both sides by 24, and then reducing 12/24, that's just 1/2. Okay, so we got our k. Now plug it all back in. Again, we're finding y when x is 10 and z is 5. So plugging this all back in to y equals kxz, you'd have y equals 1/2. X this time is 10, and then z is 5. Okay, so you plug it all back in. Y is going to equal, well, half of 10, that is 5. And then 5 times 5, you should get 25 for your y. Okay, the next one. The volume V of a cone varies jointly. Again, it's joint variation, but we're going to use their variables again. So joint variation is y equals kxz, but it says volume varies jointly, so k is still going to be there, as the area of the base B. So instead of x, we'll replace that with a B. Instead of z, we'll replace that with an h. Okay, so using their variables. So the volume is 12 pi feet cubed, b is 9 pi feet squared, and h is 4 feet. So let's plug those numbers in. Again, 12 pi is v. We need to find k. We got 9 pi, and then we got 4. Okay, so this would be 12 pi equals k. That'd be 36 pi. Dividing both sides by 36 pi, and then just solving for k. So reducing this down, the pi's cancel. 12 over 36 would just simply be 1/3. So we got our k. So we want to find b now. So finding b, so again in this equation we're finding b. We know the volume, we know the height. So plugging these all back in to the equation, the volume is 24 pi. We have k, solving for b, and h this time is 9. So we'd have 24 pi is equal to, on the right hand side, if you just multiply, that'd be 3b. And then dividing both sides by b, the area of the base comes out to, that would just be 8 pi. And this would be feet squared, since it's the area of the base. So feet squared are square feet. Okay, so we did joint variation. Now inverse. So these next ones are inverse variations. So it says if y varies inversely as x. So here's inverse variation. It's k over x. Okay, so we know y is 12 when x is 10. Y is 12, x is 10. Again, pause, solve for k. So I'm just going to multiply both sides by 10. So we get 120 equals k. All right, now use that. Now we're finding y when x is 15. So plugging this all back in, y is equal to k over x. So 120 divided by 15, and that should come out to be exactly 8. And then same thing for 10. We're doing inverse variation one last time. So y equals k over x. We have y is 16, k is 42. Again, solving for k. Multiply both sides by 42, so k comes out to be rather large, should be 672. Okay, so now use your k, plug it all back in. We're finding y when x is 14. So plugging back into the original equation, finding y. So we're just doing 672 divided by 14, and that should come out to 48. Okay. But now what is inverse variation equation? What does this look like when you graph it? So you notice you have two tables set up, right? So let's just kind of go through the basic stuff here. This is inverse, so y equals k over x. So we need to find our k value. Y is 4, and x is 5. Find k. So multiply both sides by 5, you get 20 equals k. So as an equation, here's what we're graphing. We're graphing y equals 20 over x. All right, so how we're going to graph this? Again, you have two tables set up, right? One table is going to have positive x values, one's going to have negative x values. If you notice, the one value that x cannot be in this case is x cannot be 0. So I can't plug in 0 for x. I can only plug in positive values and negative values and then solve for the y. So think wisely about this too. Think of numbers you'd want to plug in for x that make the most sense, because when you plug these numbers in, you're taking 20 and then dividing them by that x value. So numbers I would probably choose positive. I'm going to do 2. I'd probably do 4, 5, and then also 10. Okay, and then doing the same thing with the negatives, just all negative values. -2, -4, -5, -10. So I'm just trying to choose easy numbers to actually work out and do the math with. So when you plug in 2 for x, you're doing 20 divided by 2, you should get 10 for the y. Then you should get 5, and then 4, and then 2. And then same thing with the negatives, just obviously negative. So -10, -5, -4, -2. So here's what the graph looks like. This is kind of a preview as to the rest of the graphing that we're going to do throughout this unit. So graphing out these points now, going over 2, going up, 10 should be up here at the top, then over 4 up 5, over 5 up 4, over 10 up 2. So here's kind of the first piece. Okay, the second one, if we graph this, so -2, -10, -4, -5, -5, -4, -10, -2. Here's the second piece. Okay, what this is called, this overall graph, so basically if you're graphing a rational expression, if you have a variable in the bottom, this is what your graph's going to look like every time, okay, for the most part. What this is called a hyperbola. So we're going to be graphing these all throughout the rest of this unit. There's a lot more details involved, but you've at least seen kind of now the basics of what these graphs are going to look like. Okay, so once we get into our graphing unit, you will see more and more of these, making a hyperbola. But we got one last problem down here. So it says the time t needed to complete a certain race varies inversely as the runner's average speed s. So inverse again is just y equals k over x, but using their variables, t equals big K over s. Okay, so if a runner with an average speed, so speed is 8.82 miles an hour, completes the race in 2.97 hours, we want to know what's the average speed of a runner who completes the race in 3.5 hours. So it's taking them more time, right? Taking this person more time than this person. This person finished the race in 2.97 hours. Here's their speed. Okay, that's pretty darn good speed, I must say. So if I plug these numbers in, again, just plug them into the equation that we have. So 2.97, that's a time, so I'm going to plug that in for t, and that equals k over my speed. His speed was 8.82, so let's find k. Figure out what k is. Just multiplying both sides by 8.82, and you're going to want to keep the full decimal. I know it's going to be a kind of a long decimal, but to just be most accurate, keep the full thing. So these cancel, but multiplying 8.82 times 2.97, that comes out to be 26.1954. So don't round it, keep the full decimal. Okay, now use K. Again, we're trying to find what's the average speed of a runner who completes the race in 3.5 hours. So again, that's a time, 3.5 hours. I'm going to plug that in for T. 3.5 would be equal to K, is 26.1954. And then dividing that by their speed, because that's what we're solving for. Okay, so now from here, solving for s, what I would do next is I would go ahead and get s basically out of the denominator. Multiply both sides by s. So you have 3.5s is equal to 26.1954, and then dividing both sides by 3.5. So dividing by 3.5, this person's average speed, so it should be slower since it took them more time, right? First person finished the race in just under 3 hours. It took this person 3.5 hours, so their speed should be smaller, should be a lesser number than 8.82, just to make sure it makes sense. And it does come out smaller. So the speed of this runner comes out to be about 7.48 miles per hour. And there you go. All right, so there's your next lesson. Again, fairly easy. Just make sure you know those equations and which one goes with what. If you have more questions, just let us know.